Okay, we're coming up with our screen here.
Okay, let's go.
More on fuel trim. There's, a lot of times when you think you totally understand fuel trim, that's when you get blown out of the water. Anybody that ever, a lot of times when you think you know something better than you know it is when you get in trouble, And so some of the things that affect it. Now, I'll talk about airflow sensors. This is what an older vane airflow sensor looked like. This thing originally was a Bosch design, I believe. And whenever I was working at a Volkswagen dealership, there's a little screw on the side that you adjusted to trim this thing. And we would actually have to put an exhaust gas analyzer on there, and it had a little port you stuck it onto, and you were supposed to turn that little adjustment screw until your CO was at 1%. That was back in the 80s. But this particular thing, I want you to particularly pay attention to that. There was an L-shaped vane that's hooked up underneath this, and as the air came through and moved that L-shaped vane, this slid on that resistive paint, and that gave you your voltage change. It's kind of like a TP sensor, but it was driven by air. And you notice this little stiff little metal right here that's holding that set of points open. There's a little set of points there you can barely see. Now that little set of points right there is if there was no air that was going through there. This particular one's made by Nippon Denso, but it's similar to all of them that look like it. It would actually operate the fuel pump across these 2 points. So these 2 wires right here went to the fuel pump. And if you were going to unplug this thing and try to run the vehicle without it, you'd have to jump around those 2 wires at that connector. You didn't know which one they were. Don't just discriminately be jumping wires at a connector because you think it'd be I-8, because it won't. You may burn something up like that. So be careful about which wires you jump. All right. Now it's got an L-shaped vane that moves against a weak spiral spring in response to incoming air, and the signal it sends varies as the slider moves on the resistive paint. You can actually reach in there and move that thing with your finger. Now, some of the older Volkswagens had it. The very first, there was some Escort GTs that had this kind of a deal on them when I was working at Ford Place back in the early 80s. And that thing right there is almost gone now. A lot of your Toyotas used it. This particular one I took a picture of was on a Toyota MR2 that we worked on in here. That little set of points that operates the fuel pump right there. It basically gives you fuel to start with. Now this right here is a mechanical airflow system, right? It's a diagram of the K-Jetronic fuel system. And what you got right here is you got a sensor plate. Air is coming in here. It picks up on that sensor plate, which is about that big around. It's about as big around as the top of a 1-pound coffee can. It raises it up, and you notice this is the way this is shaped. The higher it goes, the less resistance it offers because air can go around it. And right over here, that's an adjustment screw right there. And so it's sitting on a little piston. And that piston, as it goes up, it opens up and lets more fuel go to the injector. There's a fuel distributor right here. And that doesn't turn or anything. It's just that each one of those lines goes to an injector. It's basically an atomizer. All right. So I worked on these over there too. They got this is one that was on the Volkswagen Rabbits that we worked on. Now the other ones I was working on was on the buses and some of the bugs and all that. But one way or another, there is also pressure right here. They're actually showing that pressure right. This pressure right here is applied by something I'm going to show you in the next slide, and it has a specific job to do. So you're basically looking at the way that the fuel distributor works, and those little ports that fuel goes through on the way out with them braided steel lines going to those atomizers. This thing runs on about 70-80 pounds of pressure, and it basically they have to be cut with lasers. I don't know, probably the same thing they do with regular fuel injectors. This is a better diagram of it. You see the air comes in here through the air filter, raises that up, that picks up on the fuel distributor, and it goes to these little atomizers. And those atomizer injectors have got O-rings around them, and they just basically pop into a little plastic thing that screws into the head. Real unusual how they do. And you can pull them out and raise that thing up when the fuel pump's running and see them spray. You got to put them in a bucket or something. And that's a pretty neat thing. Now this right here is what you call a control pressure regulator. And when the control pressure regulator is cold, it reduces the amount of pressure that goes to that piston that hydraulically pushes down on it. It kind of resists this. If it reduces the amount of pressure when it's cold, it lets it come up farther and you get more gasoline for cold enrichment. Now that doesn't stay like that very long. There's what you got is a little bimetal deal here that they got drawn, and wires coming in here, and whenever it heats up, that little bimetal strip closes this off and it gets to where it's got, the full pressure on there. This right here would be the cold start injector right there. and this is your throttle plate, and then that's a little idle air bleed and all that. That's a little overdrew of it. I mean, one way or another, let's talk about today's mass airflow strategy. Mass airflow's got priority on these systems. To measure the incoming air, the PCM does not need to know anything about throttle position, exhaust gas recirculation, engine temperature, or even barometric pressure. It does infer barometric pressure, but it doesn't pay close attention to what it is, not like it does on the other systems. And it can use other inputs to infer mass airflow if the mass airflow is disconnected. So if you disconnect it, if you think you got a problem with it, and it takes care of, like you can, these can cause a no start. I used to see some Rangers and stuff, and I'd go out there, they wouldn't start, and we had a rash of them. You unplug the mass airflow sensor and it'd fire up, and it needed a mass airflow sensor. A lot of them have a cold wire that keeps track of ambient temperature. You look down into the mass airflow sensor, you see two little wires, you see them two little wires. One of them's a cold wire. It's measuring the temperature that wire is, and it's heating the other one up to a constant differential. In other words, it's keeping it a certain amount of temperature, and how much current it has to apply to that little platinum wire is telling it how much air is going in the motor. You know, that sounds kind of complicated, but the engineers were pretty sharp at designing that thing. Now, if somebody's got an air filter that's coming apart and crud sticks to those little wires, it's going to make it run sluggish. There was an 89 Mustang. 89 was whenever Mustangs came out with a mass airflow, and they didn't have data stream yet, but they did have mass airflow starting in 89. Didn't get data stream till 94 on Mustangs. Anyway, this guy had a convertible Mustang, and he said it just ran sluggish and all, and basically all I did was pull the mass airflow off and look at down there with a flashlight, and you can see all this crud all over it, you know, like fibers from old air filters and stuff, and I washed all that off, and it ran like a new car. I think he still drives that thing, and he fixed it 10 years ago. All right, mass airflow sensors need power. You gotta have power feeding the mass airflow sensor. That is not reference voltage, that is ignition voltage. This mass airflow sensor is a device that has to be turned on by some good strong ignition voltage. If something else that's fed by this same fuse blows that fuse, then what you're gonna see here, you may pull a code that tells you got a bad mass airflow sensor. In other words, the mass airflow sensor is not putting out, and you're a dummy if you rush out there and have them order you a $175 mass airflow sensor and put it on there, and you find out it's just like it was. And then the parts house says, well, we're not taking this back because we don't know if you might burn it up. Well, that ain't what was wrong with it and all that, you know. So what you got here, you got to find out if there's power there. See that? A, B, and C? Well, that's a GM. Terminal C is supposed to be hot. If it ain't hot, you need to find out why. If that fuse is popped, that fuse incidentally on the GM car, a lot of them also feeds the oxygen sensor heaters. And I've seen a shorted oxygen sensor heater blow that fuse, and the only code we got was for a mass airflow sensor. You got it? All right. Check for good voltage at the mass airflow connector if you get a code for a dead mass airflow sensor, and check the fuse in question. All right. Unmetered air leaks. This is what we were talking about. You remember what we was talking about earlier this week? The guy said it was acting like a rev limiter. This is the kind of hogwash you see on these hoses right here. Now you may pay $100 for one of them hoses, or you can do the Jonathan thing and wrap electrical tape around it, but the right way to fix it is to go ahead and replace the hose, you know, replace the tube.
It worked until Brian got one, so
yeah. Well,
and I actually put silicone on my hand tape. So.
Yeah, you did a double whammy. We siliconed it and taped it.
Yeah.
You double whammy everything, don't you?
I guarantee you if you left it on the scar, it's still been running.
If it's a hammer, you double whammy it with that too. All right. PCM figures fuel delivery based on mass airflow readings, and will cut back on the injector pulse if you've got an unmetered air leak, and that causes an out of balance fuel mix that's picked up as a lean condition by the O2. So what kind of fuel trim numbers am I going to see if I've got an unmetered air leak? You know, so they're going to go high. It's add is correcting for a lean condition. Make sure you understand that. They're going to climb when unmetered air leaks are present, holding the throttle open a little bit. When there's an unmetered air leak, drives the fuel trims back toward normal because it sort of overwhelms the unmetered air leak. Now I will tell you, if it's a bad enough unmetered air leak and it torques and it makes it worse, you're going to feel it. But if you've got a small unmetered air leak, it's not changing because of engine torque. Whenever you raise it up and hold it up at a higher RPM, if they come back to normal, that's a pretty good piece of diagnostic information because it usually points you in the direction of an unmetered air leak or a vacuum leak. You know, if it's some other kind of system. All right, the PCM's focus, the PCM, now think about this, you might not have thought about this before. The PCM cannot do anything about the air. It's totally dependent on whatever air is coming in. It can read the air, but it can't change it. You got me?
Basically, it reads air and.
It needs to know what the air is, but if it doesn't like the air, it can do nothing about the air. That make sense? It can change the fuel all the way from shutting it completely off. You remember the strategy I told you? This one guy who told me that I was talking to him, my lunch partner, he says if I put my Camry in neutral when I'm coasting down these long hills, will it save me gas? Is it gonna save gas that way?
Because when you let off the pedal, it does the same thing.
It shuts the injectors off at a calculated pulse width of less than 1.2 milliseconds at an engine speed greater than 1200 RPM, the injectors are turned off. That's the way the algorithm used to be typed. I don't know if they still type it that way or not. But anyway, the PCM precisely controls the fuel delivered, but only when it's able to accurately measure the air entering the engine. So if the PCM doesn't like the air, it can't do anything about it. Now it can change, it actually dials fuel up and down. Now I will tell you this, why does it do anything with the throttle plate or the idle air control? What does it use those for?
To control how much air to go in it.
I mean, why does it do that though? I mean, that's an obvious answer. You just
Well,
get,
I mean,
whenever it
the
does,
air control takes up the slack of when the flap closes.
yeah, it keeps it from dying. It keeps it from dying because if you just let a flap close without having a little dash pop function, it'll die. But also, what else? Why else does it move the throttle plate to let more air in? If you're not putting your foot on the gas, if it's making the decision and you're not, under what conditions does it open the idle air control or raise the throttle plate?
So heat the engine up?
Well, you're talking about for fast idle. Is that what you're
Well,
talking
I
about?
mean, like when you first crank the motor up and it's cold.
Yeah, that's one thing. That's fast. That's one thing. But what about when you kick on the air conditioner?
Yeah.
An engine load, power steering. It's going to open it up a little bit on that. See, there's other things. It does things with the air, but it's not because of the fuel mixture. It's doing things with air to control speed, not fuel. See what I'm saying? So it can't do anything about the amount of air coming in other than the fact that it can idle it up a little bit, you know, or idle it down. Or a cruise control is done with not idle air control, but it's done with the electronic throttle body and a cable-driven thing that doesn't work anymore on the Taurus because somebody broke it off. Okay. Why do fuel trims go positive when the oil filler? This is a question for you guys. Why do the fuel trims go positive when the oil filler cap is removed with the engine running?
It has no engine back.
What? What? I
We
didn't
don't
have an
have-
answer to that.
Crank.
If that was an ASC test and there was only one question on it, you'd walk out of there with no patch, okay?
Alright, well anyway, when you pull the cap off, it's sucking unmetered air.
That's a good idea. How's it getting in there?
Because it's sucking it through where the cap goes.
How is what's coming in through the cap making it into the engine?
Through
Yeah,
the
something.
PVC valve.
Aha! That's what I kept trying, that's what I wanted you to say, through the PCV valve. So the PCV valve needs a sealed crankcase so that every bit of the air going through the PCV is going through a metered source. It's being measured. So that's why they put it in that hose between the mass airflow and the throttle body, so it'll meter that air as it's going in. You take the cap, it can get a bunch of air through the oil filler cap. I mean, if you leave the oil filler cap, it also throws a lot of oil out of the engine, and the customer's unhappy because it paints the engine compartment with oil, and I have seen one burned up for that reason, so be careful about that. All right, right here, speed density system. This method of fuel management uses a map sensor, but that's only part of it. Now, speed density, now there was a book, back whenever, in '89, there was a book that came out that was Mitsubishi published when we were selling those Eagle Summits and Eagle Talons, back whenever Jeep and Eagle were together, and I had part of that dealer franchise. And they had a bunch of the most beautiful little verbiage on that, and a lot of people don't know it, but there is a density speed and there's a speed density. Depending on your priority, there's density speed and speed density. Most of the time people just lump all those together, but some of them, like your Jeep Cherokees, like 87 to 90 model, the Bendix fuel injection system that they had, unless I missed my guess, I think that one was density speed, and most of the rest of them are speed density, so don't get too confused by that. That's basically the one that uses a map sensor. You know, but if the crank sensor is given a good bit of priority. You know, you got, because if it knows how fast it's turning and it knows what the displacement is, it can kind of figure things there. Anyway, the weight of the air is calculated just like it is on a mass airflow, but it requires a PCM to do more math. If you're a PCM that's doing math, you're going to need to do a lot of math. It's a simpler way to measure the weight of the incoming air if they use math. Well, anyway, these are all factored in on map sensor dominated vehicles, RPM, see, speed, density, engine volume. What's engine volume? I would say that's the displacement, right? How much air is going to try to go through there every time you turn it 2 times? If it's a 4 liter, it'll be 4 liters of air. Throttle plate position, manifold absolute pressure, intake air temperature, and barometric pressure. All that stuff's factored in. Unregulated fuel sources like dripping injectors, saturated canister, high fuel pressure, ruptured fuel pressure diaphragm, fuel contaminated engine oil can tip this out of balance as surely as unmetered air and will drive the fuel trim to negative. There's a dripping injector, and you got fuel here, you got a diaphragm here, this is the cutaway, you got a vacuum here. If this diaphragm fails, you're going to see vacuum in that line right there. And I have seen so much vacuum going through that line that it's hydro-locked an engine before. It's really nasty. This is a favorite failure on some of your V6 GM cars. You know, like your 3.8s and 3.1 and all that kind of stuff in the old one. I mean, that little diaphragm loves to rupture. So its vacuum is acting on that, you see, it is going to pick this up and let some of the fuel go to the turn. It's a calibrated spring, and so it's calibrated. You might notice that one right there has got an adjustment. You could break it loose and you could adjust the spring and put more tension on it if you wanted your fuel pressure to be higher, and so on and so forth. Well, yeah, it subtracts fuel to correct any time there's anything rich. If this little sucker sticks and it cannot move, and I've seen this before, that spring gets all rusty and everything, or something goes on in there. I can cut one apart. And I've actually seen them where they were talking about them puffing black smoke and all, and I'd check the fuel pressure, and even if I saw like 40 pounds of fuel pressure or 35 or whatever to start with, I'd reach over something and just tap really gently on the fuel pressure regulator, and it bounced to 100 pounds. And you knew you needed a fuel pressure regulator. Now, like I say, if you check it real quick, one of the worst things you can do is have a problem that's fuel pressure related, but not check it while the problem is present. If you just hook up the fuel pressure, you go, oh, got good pressure, pull it off and throw it on the bench, and then the fuel pressure concern happens when you're not looking, you know, and you weren't having if you're not watching it while it happens, you may misfire on your diagnosis. That's why if you're checking an electrical problem, you need to have some indicator, if it's a light, a buzzer, or whatever it is that you're working with, it's going to light off if that problem happens. Like if I'm pulling on a wire harness and I got a test light set up so that it'll come on when the wire harness short happens, and I'm watching the test light while I'm manipulating the harness, all of a sudden, boop, boop, there it is. You can go right to it that way. See? Anyway, you need to be watching it while it happens. That's the point. All right. Short fuel trim, instantaneous fuel pulse width adjustment to what the O2 sensors are telling the PCM. Short fuel trim is what it's doing right now. If you watch the little camel hump of the oxygen sensor going up and down, you'll see the fuel trim following right behind it. The short fuel trim following right behind it. All right. The long fuel trim is the adaptive memory part of the picture, and follows short fuel trim makes course adjustments to fuel delivery algorithm. Long fuel trim's at 0, short fuel trim tops out. Long fuel trim says my little friend is not able to handle this, so it starts clicking up, and adding more fuel, you know, just changing the formula all the way up. And when it gets up here in the range where the short fuel trim is, the short fuel trim goes back to 0. And whenever you're looking at a system, if you look at the scan tool and you see long fuel trim way out of kilter, you're probably going to see short fuel trim close to 0. All right. So if short fuel trim is close to 0, long fuel trim is way out of line, you need to go find out what's causing it to correct for a rich condition or correct for a lean condition. Most of the time, you'll be correcting for a lean condition. Now, let me ask you this: what did you see for fuel trims on the Chevy? You remember when we first started looking at them? Did you write that down?
Yeah.
They were positive, weren't they? You were seeing plus 25 consistently. When we got through working on it, they were 0, right? Long fuel trim and short fuel trim were 0. Why were they plus 25 on the 4.8?
Remember?
3 of the injectors were totally clogged, so it couldn't put nary a drop of fuel in 3 of those cylinders, and so it was driving the fuel rich. Now, if it's driving it lean, you may have 3 of them dripping. See what I'm saying? So there we go. All right, just remember that how it worked. Now, for the people that like to spend lots of time enjoying the cool AC, sitting in the car pretending to look at the scan tool screen, and we have, there's quite a few people like that, I mean, this is like the thing where I go over there and say, what are you doing? I'm helping him. I was telling him the other day, the oldest trick in the book. And I say, what are you helping him do? Oh, we're doing this, And then so I turn my back and I walk away, and when I glance back over there, he's standing here like this again, shooting the bull. Or if I go over here to the car and somebody's sitting there, or they're sitting at a computer and there's nothing on the screen, it's totally white except for one little piece of text up there that he could have read 10 times or 15 or 30. And I go in here and just got his head into his cell phone. Go in here, I tap on the glass, I said, yeah, I got that. Points at the computer screen. And it's like pointing at the scan tool screen, I mean, the phone disappears whenever I walk over the window. Anyway, there's only so much you can figure out sitting on your fanny with a scan tool. Sometimes I give one to somebody and I'll say, I need you to find out what's going on with this car. It runs like crap. Well, the car's running like crap, the hood's closed, somebody's sitting in the car just looking at the scan tool for 30, 45 minutes. What are they learning? I don't know. I don't spend that much time looking at a scan tool without opening the hood and at least having to look around under there and see if I can see what I can see, you know what I mean? I want to get my hands on something. Pretending to work while playing with your phone doesn't work either, okay? Now, how much can the MAF system know? If there's an exhaust restriction downstream of the catalyst, like an internally damaged muffler with a baffle that's partly covered, what's the engine can't breathe out? See if it can't breathe out well. Can we find that with the scan tool?
Or you could watch a fuel time.
Can you? All right, look at here. On this Ranger, Alvin Moore, who's another guy that rides for motor rage like I do, he put a man-made exhaust restriction in place, and it exhibited low power, and the only PID that changed was the load. He put an exhaust restriction in there. I don't know if he put a Tata in the tailpipe or whatever he did. Reading 74% when it should be reading closer to 95%. Right? That's the only thing that changed was the load. You gonna go look at the load and tell me you got an exhaust? I don't think so. All right, the MAF had no knowledge of the exhaust restriction. It's still measuring incoming air, even if it's not able to breathe out there, right? All right, his Envoy, he did the same thing on that, and I sort of blew these up so you can see them better. All right, it was bugged with the same kind of exhaust restriction. You got RPM, it went up. See, it was struggling to stay at 60 miles an hour, but the data PIDs didn't show anything out of the ordinary. Right, there's your TPS, you got it wide open throttle there, see 100%. All right, on this particular here, you got engine load, 99%. MAP is it, 28.6. You can look at these right here. Look at the fuel trim. What are you seeing there? This is whenever he was struggling to stay at 60 miles an hour. I'm seeing long fuel trim close to 0. I'm seeing short fuel trim close to 0. All right, look at this right here. Oxygen sensor, full rich. Oxygen sensor 2, it would show rich 2. Got it? Both do the same way. All right? And look at that right there. Closed loop. It basically did power enrichment right there. Power enrichment, it did that. All right. Now right here we got airflow. So your airflow is 179, which it went up pretty strong. And your vehicle speed, it was really busting their fanny on that as fast as they ever went with 66 miles an hour on that. All right. Now the Ranger, he did the same thing on his Ranger. It barely even noticed the plugged exhaust, and the scan tool PID didn't show it either. See there? All right. See what you got going on there? There's your load. There's your mass airflow, grams per second. All right, do you see, notice you got minimum, maximum, and current. Current is what you're seeing now. Maximum is as high as it's ever been, and minimum is low as it's ever been. Fuel trims. They weren't really so terribly bad. They were a little down, but not much, All right, so here you got your oxygen sensor. It went rich, just like the Envoy did. It dropped into open loop when he went to wide open throttle. All right, and here we go with your long fuel trim. Now, long fuel trim went up to 8 when it was in open loop and he was at wide open throttle because he was at power enrichment. Short fuel trim did too. O2S1 mirrored O2S2. All right, so it's wise to get accustomed to what the scan tool data looks like when there's a vacuum leak, and the effect is slightly different. Now, this the exhaust restriction is gone. We're going to put a vacuum leak in here. Slightly different on MAP systems instead of MAP system. The red line is placed at the point where a vacuum leak was introduced. Now, what happened here? Short fuel trim went up. You got that? Look at that. For a moment, the oxygen sensor dropped into the basement. But then it recovered. Why? Because long fuel trim went up. See how I was telling you that earlier? It starts stepping up, and it gets it to where that one will go back now. And here we are. Once again, you're looking at the same deal here. Low fuel trim 2. Notice that short fuel trim immediately went high. This one here just briefly went lean. Okay. The vacuum leak created on the Envoy is so the PCMs close the electronic throttle plates because the idle speed thing, and it picked up when it closing the throttle plates can't control the engine speed. Now listen to this. This is important. The injectors are turned off by the PCM on most of the platforms. If it can't control the idle speed, it gets scared that you're going to crash and burn, and it shuts it down. All right, the vacuum leak was really bad. And see, as you can see TPS right here. It went off. Injector pulse width. See how I was jacking around with that? Oxygen sensor went really, really lean when it did that. All right, now early GM vehicles back in the 1980s dumped MAP in flavor of meth. You know what I'm saying? In other words, they got rid of MAP and they put MAP on there. That's what one of their sensors looked like back then. And it had a kind of a burn-off circuit. When you turn it on, it'd get really hot and burn the dust off of it. It's really cool to watch that. But whenever it wasn't running right, GM said to whack the mass airflow sensor and see if it ran better. And if it did, you had to put a mass airflow sensor on it. Then they came out with a retrofit and put MAP sensors back on some of the early platforms. But a lot of them today have a MAP and MAP, right? Some, like most Chrysler products, though, stayed away from mass airflow and stayed with MAP. Now, MAP's a good way to check for EGR activity, but it can also be used in case of mass airflow failure. That's what the MAP sensor looks like, and there's your mass airflow up on that Oldsmobile. Altitude issues in atmosphere, you got 21% oxygen, 1% inert gas, and 78% nitrogen. Whether you're at the sea level or at the top of a mountain, the mix of the air is the same. It's just that there's not enough pressure, and the engine needs pressure differential in order to get that air to come on in. If you got lower pressure, like if you're really high altitude, you're going to notice the car running like a three-legged dog. That is 72 Chevrolet that I was driving one time. Me and my mama went to the Grand Canyon on it, and the rim of the Grand Canyon is 8,000 feet above sea level, and that thing wouldn't hardly pull your hat off. And you know, it was a Chevrolet, but it still ran pretty good whenever we were at normal altitude. All right, so while a turbo might adapt to this change, it's still effective. So a modern EFI system can add and subtract fuel, and all vehicles tend to lose power proportionally with altitude. If you go high enough, it won't run at all. In the old days, vehicles that were going to reside at higher altitudes needed altitude modifications, ignition time and fuel mix to minimize power loss. Electronic fuel injection systems also need mods for altitudes above 4,000 feet. Up to 4,000 feet, the PCM can deal with it, but the mass airflow sensor on non-MAP vehicle infers it by calculating. This is what MAP sensors look like. This one here is a Ford one that operates on a frequency. On this frequency right here, 159 hertz when you first switch on the key is sea level, more or less. And then whenever you crank it up, and it's reading it through in the manifold through that hole right there. When you crank it up, it's basically going to drop down to about 110 hertz usually. And you got to have a meter that'll read hertz if you're going to measure that. These other ones measure voltage, and some of them go right into the manifold, some of them have a line hooked to them and all that. Now, if you find a fuel trim related concern, you think you fixed it, do a fuel trim reset with a scan tool or by disconnecting the battery. After you're done with your repairs, you restart the vehicle and watch for closed loop. When closed loop happens, if the short fuel trim starts walking away from zero, you're not done. You're going to have to go back and work on it some more. Fuel trims plus 27. I was there. Technician tosses an O2 sensor at it. I'm not the one that did this, okay? Now, I'm not saying I've ever put a part on that. I was not going to fix it, but anyway, I didn't this time. Barometric pressure pit is reading 24 inches. Should be reading nearly 30. Baro readings will change when there's a storm, so don't be confused by that. And when pressure, the fix was to replace the MAP sensor, which was miscalculating barometric pressure. He was thinking since we'd seen so many oxygen sensors fail, that's what it was. You got that? Everybody happy with that? Everybody knows something now you didn't know when you came in here. Did you like digging deeper into the fuel trim? Were you bored with it? You all look like a bunch of skeletons. All right? I needed some donuts. That's the end of the slideshow. All right. Whoops. All right.